Welcome back to Introduction to Higher Mathematics. In our last lecture, we explored number theory, which focuses on the properties of numbers themselves, especially the integers. We began our discussion by looking briefly at the history of our understanding of numbers, how negative numbers, something we take for granted, weren't as obvious a long time ago, and how imaginary numbers were equally regarded with disbelief and skepticism. We then started with the simple concept of divisibility, and from there saw how Euclidean division lets us divide a by b to get a quotient q and a remainder r. After mentioning the greatest common divisor and least common multiple of two numbers, we saw how to use Euclid's algorithm, in which we can find the GCD of two numbers via repeated division, without ever actually having to find the factors of either number. We talked about how to solve simple Diophantine equations, equations in which we're only concerned with integer solutions, using Euclid's algorithm. From there, we turned our discussion to those elusive beasts known as prime numbers, divisible only by themselves and 1. We defined Euler's phi function, which counts the number of positive integers less than or equal to a number n that are relatively prime to n, and the prime counting function, which counts how many primes are less than or equal to n. Finally, we saw just how difficult the quest is to actually find the prime numbers. For this lecture, let's think back to Euclidean division. Recall that given two integers a and b, as long as b is not 0, we can represent a in the form q times b plus r, where r is less than b. Let's look at what happens if we let b equal 5 and let a change its value. If a is 0, then 0 equals 0 times 5 plus 0. If a is 1, then 1 equals 0 times 5 plus 1. 2 equals 0 times 5 plus 2, 3 equals 0 times 5 plus 3, and 4 equals 0 times 5 plus 4. Now, if we let a be 5, then the quotient changes to 1, but the remainder reverts back to 0. After this point, the process starts all over again. 6 equals 1 times 5 plus 1, 7 equals 1 times 5 plus 2, 8 equals 1 times 5 plus 3, and 9 equals 1 times 5 plus 4, until 10 equals 2 times 5, with, again, a remainder of 0. So if we keep on increasing a, the remainders follow a cyclic pattern, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, and so on. Now, what we can do here is we can create a new number system using just these remainders, in which the numbers wrap around back to 0 once they reach a certain point. What's more, these remainders work according to a new set of rules called modular arithmetic. You may not know it, but you've seen modular arithmetic before, and work with it in your daily lives. Young children internalize modular arithmetic when they learn how to tell time. A question we might ask a young student is, if it's 9 o'clock now, what time will it be 4 hours from now? Assuming they're on the 12-hour system instead of the 24-hour system, they would know that after they reach 12, they need to wrap back around to 1. What's more, the days of the week act just like the remainders when we divide by 7. If we let Sunday correspond to 0, Monday to 1, Tuesday to 2, see what I did there? And so on. So let's make some definitions, and introduce the concept of congruence modulo m, where m is some natural number. We say that two integers a and b are congruent modulo m if a minus b is a multiple of m, which we call the modulus. So for example, 42 is congruent to 27 modulo 5, because 42 minus 27 is 15, which is indeed a multiple of 5. Most mathematicians write this congruence like this, where instead of an equal sign, we use 3 bars, which is read as is congruent to. In addition, we often shorten modulo to mod, and put this part in parentheses at the end. However, I personally prefer a different notation. I use the same congruent symbol, but I put the modulus m as a subscript under the congruent symbol. I like this notation a lot because it better keeps the congruence relation in the same place, making it a bit more compact, rather than having it split between two different parts of the expression. But what does this have to do with remainders? Well, look at what happens if we use Euclidean division to divide each number by our modulus. 42 divided by 5 is 8, with a remainder of 2. And 27 divided by 5 is 5, also with a remainder of 2. So we can alternatively say that two integers are congruent modulo m if they both give the same remainder when divided by m. By the way, As a side note to computer programmers, if you've done programming before, you may be familiar with a mod function, often represented with a percent sign, which returns the remainder when A is divided by B using Euclidean division. This is related to congruence modulo M, but it's a little bit different. While congruence modulo M is a relation, mod in computer science is an operator. This is a subtle difference that is important to notice. So let's look at 4 fundamental properties of congruence modulo M. Suppose A and B are congruent mod M, and C and D are congruent mod M. First, we can multiply both sides by a constant k, and the congruence will still hold. Ka is congruent to Kb mod M as well. Then we can add the two congruences just like we might add two equations. A plus C is congruent to B plus D mod M. Third, in the same situation, we can also multiply the two left sides by the two right sides. A times C is congruent to B times D mod M. Finally, we can easily modify the third property a bit to talk about powers. If A is congruent to B mod M, then A to the n is congruent to B to the n mod M for any non-negative integer n. Let's look at some examples to see how this is true. We know that 42 is congruent to 27 mod 5. So what if we double both of them? We'll have 84 and 54, both of which have a remainder of 4 when divided by 5. Now, we can also easily verify that 13 is congruent to 38 mod 5. So let's combine these congruences. First of all, adding them, we have 42 plus 13 equals 55, and 27 plus 38 equals 65. Both of these have a remainder of 0 when divided by 5. Second of all, multiplying them, we have 42 times 13 equals 546, and 27 times 38 equals 1026, both of which have a remainder of 1 when divided by 5. Finally, let's raise 42 and 27 to the 7th power. 42 to the 7th power equals 230,539,333,248, and 27 to the 7th power equals 10,460,353,203. Daunting numbers, but all we need to do is look at the last digit of each to see that both of them will have a remainder of 3 when divided by 5. So there we go. All 4 of our properties have been demonstrated. Now, with all this talk about congruence, a question might have popped into your heads. The congruent symbol sure looks like an equal sign, but the question is, does it act like one? In other words, is congruence modulo M an equivalence relation? Absolutely. It satisfies all 3 properties. Congruence modulo M is reflexive, symmetric, and transitive. So, as we said when we talked about equivalence relations in Lecture 8, the equivalence relation of congruence modulo M partitions the integers into M distinct equivalence classes, which in this case we actually call congruence classes. We can denote the congruence class of some integer A modulo M with brackets, using M as a subscript. So, this congruence class is the set of all integers B such that A is congruent to B mod M, the set of all integers that give the same remainder as A does when we divide by M. So, for instance, consider the integers modulo 2. Then there will be 2 congruence classes mod 2. The class of 0, which contains the numbers that give a remainder of 0 when divided by 2, and the class of 1, which contains the numbers that give a remainder of 1 when divided by 2. So the congruence class of 0 mod 2 is just the even numbers, and the congruence class of 1 is just the odd numbers. So, what's the congruence class of 2? Well, 2 gives a remainder of 0 when divided by 2, so it's also the even numbers. In other words, there's an infinite number of ways to represent any given congruence class, since each congruence class contains an infinite number of elements. That being said, we could say that the simplest member of each congruence class to deal with is its smallest non-negative member. We call this member the principal representative of our congruence class. As it turns out, the principal representative of each congruence class is just the remainder when divided by M. So with the idea of congruence mod M as an equivalence relation under our belt, let's look at what happens when we do algebra using congruence mod M instead of an equal sign. A linear congruence is a congruence of the form AX is congruent to B mod M. When we solve such a congruence, we won't get just a single answer. but rather an entire congruence class of examples. Consider the congruence 2x is congruent to 3 mod 5. Because of our rules from earlier, we can add a multiple of our modulus to either side of the congruence and leave it intact. So let's add 5 to the right side of the congruence. Now we have 2x is congruent to 8 mod 5. Now we have a clear solution. If we let x equal 4, then the congruence is satisfied. But 4 isn't the only solution. For example, what about 19? 2 times 19 is 38, which when divided by 5 is 7 with a remainder of 3. So anything in the congruence class of 4 would solve our equation. In general, if x0 is a solution to ax is congruent to b mod m, then all the integers in the congruence class of x0 will also be solutions. Now look at another congruence. 3x is congruent to 3 mod 9. One obvious solution is to let x equal 1, and so everything in its equivalence class will also be a solution. But there are actually 2 more solutions that are from different congruence classes. We can let x equal 4, in which case 3x equals 12, which divided by 9 is 1 with a remainder of 3. And we can let x equal 7, in which case 3x equals 21, which divided by 9 is 2 with a remainder of 3. So the full solution set for this congruence is the union of 3 different congruence classes mod 9, those of 1, 4, and 7. Consider one more congruence. 3x is congruent to 2 mod 6. Letting x equals 0, we get 0, which doesn't work. What about x equals 1? That gives us 3, which doesn't work either. How about x equals 2? Well, 3x equals 6, but that's congruent to 0 mod 6. That looks familiar. Maybe x equals 3. 3 times 3 is 9, but that's congruent to 3 again. As it turns out, no matter what integer we let x be, we can only ever get numbers that are congruent to 0 or 3 mod 6. So it turns out that this congruence has no solution. 3x will never be congruent to 2 in mod 6. So under what conditions will there be a solution? Well, if we let d be the greatest common divisor of a and m, then the congruence ax is congruent to b mod m will only have a solution if d divides b. So in our case, the GCD of 3 and 6 is 3, but 3 does not divide 2, so we can see that the congruence has no solution. We can also use the greatest common divisor to further elucidate the solutions of a congruence. Again, suppose x0 is a solution to ax is congruent to b mod m, and d is the greatest common divisor of a and m. Then we can add or subtract m over d to x0 any number of times we want, and we'll still have a solution. So every possible solution to the congruence will be of the form xi equals x plus m over d times I, where I is any integer. What's more, when we solve such a congruence, our solutions must span d different equivalence classes. So in our example from before, 3x is congruent to 3 mod 9, since the greatest common divisor of 3 and 9 is 3, we should expect 3 different congruence classes for our solutions. Once we've found x0 equals 1 as our first solution, we can also find x1 equals 1 plus 9 over 3 times 1, which is 4, and x2 equals 1 plus 9 over 3 times 2, which is 7. Just as we found earlier. One word of caution, by the way. In general, you cannot just cancel to solve congruences like you can in regular algebra. If we had divided both sides by 3 in our example, we would have obtained x is congruent to 1 mod 9, which only has one congruence class in its solution, the congruence class of 1. We would never have found the other 2 solutions. The only time you can cancel a factor from both sides of the equation is if the number you are canceling is relatively prime to your modulus. So we could cancel out the 2's in the congruence 2x is congruent to 4 mod 5, giving us x is congruent to 2 mod 5. The solution would just be the congruence class of 2. Let's look at what's actually going on behind the scenes when we're canceling in modular arithmetic. Remember that when doing modular arithmetic, since we're only working with integers, we may not always be able to divide both sides by a particular number, because doing so may give a non-integer answer. What we can do, however, is multiply both sides by a particular number. Recall from good old algebra that if we're solving an equation like 2x equals 4, we divide both sides by 2. But this is really the same thing as multiplying both sides by the rational number 1/2. Since 1/2 times 2 equals 1, we call 1/2 the multiplicative inverse of 2 in the real numbers. So look back at our congruence. 2x is congruent to 4 mod 5. Is there anything we could multiply 2 by to get a different number that'll be congruent to 1 mod 5? Well, look what happens if we multiply both sides by 3. We get 6x is congruent to 12 mod 5. But since 6 is congruent to 1, we can change this to 1x is congruent to 12 mod 5. And since 12 is congruent to 2, we can arrive at our solution of x is congruent to 2 mod 5, which is exactly what we got before. When we have a number a, if we can find an x such that a times x is congruent to 1 mod m, then we say that x is a multiplicative inverse of a mod m. Not every number necessarily has a multiplicative inverse mod some m, though. But by our result earlier, we can find out just when we will have an inverse. The congruence ax is congruent to 1 mod m will have a solution if and only if the greatest common divisor of a and m divides 1. And since the only number that divides 1 is 1, we can conclude that a and m must be relatively prime. An interesting application of modular arithmetic is we can use it to find easy divisibility tests for all sorts of numbers. You may remember that an integer is divisible by 3 if all the digits add up to a multiple of 3. For instance, consider the number 6,717. 6 plus 7 plus 1 plus 7 is 21, and 21 is a multiple of 3. So we should expect 6,717 to be a multiple of 3 as well. Sure enough, 6717 equals 3 times 2,239. Though this may seem like nothing more than a neat trick, we can actually prove it using modular arithmetic. When we write out a number in the decimal system, we are basing that number on powers of 10. Let's say I had a 3-digit number ABC, where A, B, and C are digits, not factors. This number could be written as 10 squared times A, plus 10 to the first power times B, plus 10 to the 0 power times C. Remember that anything to the 0 power is 1. If this number is divisible by 3, then it must be congruent to 0 mod 3. Make sure you understand why this is true. Now 10 equals 3 times 3 plus 1. So 10 is congruent to 1 mod 3. But if that's the case, then we can raise both sides to the n power, meaning 10 to the nth power is congruent to 1 to the nth power, mod 3. Since 1 to the n equals 1 for all n, we can see that all powers of 10 will also be congruent to 1 mod 3. This means that if our number 10 squared times a plus 10 to the 1 times b plus 10 to the 0 times c is congruent to 0 mod 3, then 1 times a plus 1 times b plus 1 times c should also be congruent to 0 mod 3. Thus, the sum of the digits a plus b plus c should be a multiple of 3 as well. This same argument can be extended to any number of digits. Let's take a moment to look at another very important application of modular arithmetic: RSA Public Key Cryptography. RSA is an acronym of the names of the 3 people at MIT who developed the algorithm: Ron Rivest, Adi Shamir, and Leonard Adleman. It's widely used as a way to encrypt all sorts of text and data, and as said in the last lecture, depends on the fact that it is difficult for even the world's most powerful computers to factor large enough numbers. In RSA, there are 2 keys, a public key and a private key. The public key is open to anyone and is used for encrypting messages. The private key, on the other hand, is necessary to be able to decrypt the message. The RSA process can be broken down into 3 parts: key generation, encryption, and decryption. To invent the public key, first we need to choose 2 primes, P and Q. For security, they should be sufficiently large. Now we compute n equals P times Q. This n will be the modulus for both the public and the private keys. Next, we find the Euler phi of n, which, since P and Q are prime, will be equal to P minus 1 times Q minus 1. Now, we need to find an integer e such that e is strictly between 0 and phi of n, and e and phi of n are relatively prime. This e is the public key exponent. We now have the public key, the ordered pair n-e, that is, the modulus and the exponent. Anyone can know what they are. But we also compute d, the multiplicative inverse of e mod phi of n. This is the private key exponent, which is kept secret. Now, suppose we want to encrypt a message unit m, where m is a positive integer of some sort, perhaps found by converting a single character to an integer via schemes such as ASCII or Unicode. Also, m should be less than n, so we should keep that in mind when choosing our p and q. Otherwise, multiple characters would map to the same number. To encode our message, we find a c, such that c is congruent to m to the e power mod n. This c is the encrypted message that is sent out. When a recipient gets the message, they must know the private key exponent d. Then they would compute the remainder when c to the d is divided by n. This will turn out to be the original message unit m, since m is congruent to c to the d mod n. And that's it. RSA encryption in a nutshell. The system itself is incredibly simple. We just explained it in a matter of minutes. But then why is it so effective? Well, for somebody to be able to crack a code without already knowing the private key, they would need to be able to factor n into its original primes, p and q, and then compute the private exponent themselves. But this can prove to be a virtually impossible task when the primes being used are literally hundreds of digits long. Choose big enough primes, and even the fastest computers today would take more than the life of the entire universe to factor their product. So far, we've been working with a set of integers and looking at their properties under the equivalence relation of congruence modulo m. But as humans are clever creatures, we can take this one step further and abstract it. Rather than just working with integers, we can actually work directly with entire congruence classes, treating them as single objects of their own, adding them, subtracting them, multiplying them, even raising them to powers directly, completely bypassing the integers that underlie them. Remember that congruence modulo m partitions the integers into exactly m congruence classes. If we take the set of the congruence classes of all possible remainders, that is, all the integers from 0 to m-1, we have created an entirely new number system called a residue system mod m. Since this came from the integers modulo m, we give it its own symbol, zm. This z is the same double-struct z that we use to denote the set of integers. Now we need to define the operations of addition and multiplication on this new residue system. The properties of modular arithmetic set us up perfectly for this. If we have two congruence classes, the class of A mod m and the class of B mod m, then the sum of those two congruence classes will be the congruence class of A plus B mod m. Similarly, the product of those two congruence classes will be the congruence class of A times B mod m. So for instance, suppose we're dealing with the residue system Z5. Then for instance, the sum of 3's class mod 5 and 4's class mod 5 is 7's class mod 5, which is the same as 2's class mod 5. Similarly, the product will be 12's class mod 5, which is also the same as 2's class mod 5. Now for this to work, this should mean that if we choose any number congruent to 3 mod 5 and add it to any number congruent to 4 mod 5, our sum will still be congruent to 2 mod 5. The particular number we pick from each congruence class shouldn't matter. This is what we mean when we say that the operations of addition and multiplication in Zm should be well defined. No matter what representatives of A's congruence class and B's congruence class mod m we choose, the congruence class of our sum A plus B should always be the same. So let's prove that addition is well defined in Zm. Suppose that A's congruence class and X's congruence class mod m are the same, and B's congruence class and Y's congruence class mod m are also the same. That means we know that A is congruent to X mod m and B is congruent to Y mod m. Because of our properties established earlier, we know that A plus B is congruent to X plus Y mod m. So the congruence class of a plus b mod m is the same as congruence class of x plus y mod m. See if you can similarly prove that multiplication in Zm is also well defined on your own. Once we understand that in Zm we're actually working with congruence classes directly, we can simplify our notation greatly by dropping the brackets and the modulus, and simply work with the remainders themselves. And Zm can instead simply be represented as the integers from 0 to m minus 1. So for instance, we'd say that in Z5, 3 plus 4 equals 2, and 3 times 4 equals 2. Though this may look strange at first, it's actually quite easy when you get the hang of it. In fact, when you're doing clock arithmetic, and you say that if it's 9 o'clock now, it'll be 1 o'clock 4 hours from now, you've said that in Z12, 9 plus 4 equals 1. We can also use this notation to more simply define addition and multiplication. A plus b is the remainder when a plus b is divided by m in the integers, and a times b is the remainder when a times b is divided by m. Also note that by moving from the integers to a residue system mod m, we've gotten rid of the somewhat cumbersome to say congruence and can use a simple equal sign. We can even create tables for addition and multiplication in Zm. Take a look, for example, at the addition table and multiplication table for Z5. Notice that in our addition table, once we hit 5, we wrap back around to 0 and go on from there. Also, the multiplication table is definitely a good bit more interesting looking. Think about how strange it will sound to your friends when you can assert that 2 times 4 equals 3, at least in Z5. By the way, remember how we talked briefly about multiplicative inverses mod m, and how some numbers have them and some don't? Look closely at our multiplication table. It turns out that every number in Z5, except for 0, has a multiplicative inverse, because there's always something we can multiply each other number by to get 1. 1 times 1 is 1, 2 times 3 is 1, and vice versa, and 4 times 4 is 1. But now, let's look at the multiplication table for Z6 instead. In Z6, besides 0, there are certain numbers, 2, 3, and 4, that no matter what we multiply them by, we can never get 1. So in Z6, not every non-zero element is guaranteed to have a multiplicative inverse. So what makes Z5 so special? Simple. 5 is a prime number, while 6 is not. In the residue system ZP, where p is a prime number, then remember that Euler phi of p is p minus 1, because all numbers below p are relatively prime to p. If m is composite, though, as we saw earlier, the congruence ax is congruent to 1 mod m has no solution if a and m are not relatively prime. So we can see that Zp is very special in that every non-zero element must have a multiplicative inverse. Well, that's it for this lecture. Next time, we're going to be leaving the world of the finite and beginning to wrestle with the infinite. See you next time.